Oops. Okay. Hello, everyone. Welcome to another episode in my efforts to go through the 12 chapters of this fine book here, which will have been published 20 years ago on May 14th. So this week, we are going to talk about chapter 12. Chapter 12 is the biggest and sort of the boldest of the chapters in the book. It's kind of the what the book has built up to. It's the final chapter. It's what the book builds up to. It's also the longest chapter, and I don't think we're going to get through it all today. And I expect we'll pick it up again, perhaps maybe next week. So, chapter 12 is about the principle of computational equivalence. And the principle of computational equivalence I see as being kind of the big summary of sort of the big principle about the computational universe, the big sort of organizing principle that allows us to understand what happens in the computational universe. It has a role in NKS, in new kind of science, that might be a little bit like the role that something like natural selection plays in understanding biology, or the second law of thermodynamics plays in understanding things about statistical mechanics and heat and so on, or the role that something like conservation of energy plays in the earlier history of mechanics and so on. It's a big, bold organizing principle that connects a lot of kinds of things together. So let's take a look at what the book says about it. So again, it's the final chapter of the book, what sort of builds up to it is sort of the observations of the computational universe that were in the early chapters here, and then the application of those observations to the natural world. That sort of builds up to this big connection between those observations of the computational universe and their applications to the natural world, builds up to how those connect together in the principle of computational equivalence. So let's look at that chapter. We're talking about sort of what's the basic idea of this principle? What is the principle? What does it really say? Is it even true? And then what are some of its applications? So we're going to build up to sort of what the principle is. Then we're going to talk about for example, how does it explain what, for me, was kind of the original starting question that led to the NKS book? Where does complexity in nature and the world come from? And that's something which, as we can see, by the time we have this principle of computational equivalence, that's sort of a two-page discussion, how that happens. Then I talk about computational irreducibility, which I think is a very key concept of the science built in new kind of science. I think computational irreducibility is the kind of thing that, just as, in Newtonian science, for example, one learned about things like momentum and energy and so on, and those became concepts that were applicable not just to the specifics of mechanics, but more broadly. So it is with computational irreducibility. It's a concept that is very broadly applicable to lots of kinds of things. And we've seen the importance of computational irreducibility show up all over the place over the last 20 years, somewhat exotically in things like proof of work for blockchains and so on, but also in just ways of thinking about lots of kinds of things. And I think computational irreducibility will prove to be even more important as we go forward and we try and understand about, the ethics of AIs or fundamental questions of philosophy and so on. Computational irreducibility is a key scientific piece of input for those kinds of things. And one of those kinds of things, which I talk about in the book, is the phenomenon of free will. Then slightly more technically, I discuss undecidability and intractability and their relationship to computational irreducibility. Then there's a big chapter, big section here, implications for mathematics and its foundations, that I think when I was writing the NKS book, I kind of backed into this particular section because I wanted to say something about it. But then, as you can see, that section became quite big. And in fact, now that section, with the things we've learned from the physics project, has kind of exploded into this physicalization of metamathematics that I've written a very long piece about recently. It's more like a 200-page piece about that recently. Okay, so then this principle of computational equivalence, as I say, is a very broad thing that has a lot of implications in a lot of places. I have a section here about intelligence in the universe, very direct application. That concept of using the principle of computational equivalence to talk about the nature of intelligence was actually something that philosophically led me, for example, to decide a number of years after the finishing of the NKS book that Wolfram Alpha, a thing like Wolfram Alpha, must be possible. That was something that was sort of the result of essentially a philosophical development from the NKS book. Although, as is so often the case, that historical connection I can only make in retrospect. I'm not sure that I could have necessarily made that at the time. Talk briefly about implications for technology, and then talk about general historical perspectives on the principle of computational equivalence. All right, let's jump in. And by the way, this chapter, not only does it have lots of main text, about 120 pages of main text, it also has by far more notes. I don't think it's more notes than all the other chapters put together, but it's a lot of notes. So anyway, let's start off here. So we're talking about this idea of computational equivalence. What is it? The first question is, how do we talk about things in the world, in nature, things that we can abstractly imagine? And the first section here is talking about computation as a paradigm for thinking about those kinds of things. We could describe, in the past we could say, well, these are the rules for something. This is a set of laws, let's say, human laws, or this is the way we observe some system in nature to work. One of the points here is that this notion of computation, this notion of computational rules, is something that transcends those kinds of descriptions. It is a general way of giving sort of a description of this idea of something that operates according to a set of rules. And that can be applied to rules in nature, natural laws. It could be applied to human laws. It can be applied to things in mathematics and so on. But there is an overall framework, this notion of computation, that encompasses all of these different kinds of things. So that's the first thing to realize about. That's sort of the starting point for the principle of computational equivalence. You're not separately talking about what happens in nature, separately talking about what happens in mathematics, separately talking about what happens in a program, for example. These are all things that you can describe in a common framework, and that framework is computation. Okay, so then what does the principle actually say? Well, I start off talking about what it asserts is that when viewed in computational terms, there is a fundamental equivalence between many different kinds of processes. I say there are various different ways to state this, but it says that processes that are not obviously simple can be viewed as computations of equivalent sophistication. And I comment here, I haven't read these words in a long time. At first, the statement might seem vague and perhaps almost inconsequential. We will see in the course of this chapter that, in fact, it has many very specific and dramatic implications. So first thing to realize is, why might it not be true? Well, it could be the case that as we make up computational systems built according to rules, and we look at, well, what level of computational sophistication is achieved by these different rules, there might be a kind of a whole collection of different levels of computational sophistication, none equivalent to any other. It might be the case that gradually, as you add more to the rules, you would gradually get progressively greater computational sophistication in what these rules do. But what the principle of computational equivalence says is that that isn't the case. That what's going to happen is, as soon as you reach above some very low threshold, every kind of thing that you can construct with computational rules is going to correspond to a computation of equivalent sophistication. If you I talk here about what might lead one to an idea like this, and one piece of it is the idea that came from the 1920s and 1930s the idea of computation universality, the phenomenon of universality, the notion that you can, this idea that you can reach a certain level of computational sophistication where everything is equivalent, where you've reached the sort of maximum level of sophistication. That's an idea that is closely related to this idea of universality. That is, once you have that computational system, be it a Turing machine or a combinator system or whatever else, which is universal, then there is a way of setting up the encoding for that system so that it can emulate any other system that we consider computational. So that notion of universality makes it, that's the first thing that makes it not completely kind of crazy to say, well, when we build up these systems, they might be able to be just equivalent in their computational sophistication. But the point that I make here is that the thing that led me to that idea is noticing that all these different systems that I studied in the earlier parts of the book, even though I kept on saying this system is way too simple, there's no way this system does something sophisticated, but then it turns out it does. And then in some cases, it turns out one can actually prove that it's universal, prove that it's as sophisticated. What it does is as computationally sophisticated as anything else. But as an observational matter, when you just look at millions of pictures of these different kinds of systems, you quickly get the sense that either I can see what it's doing, I can understand it, I'm sort of smarter than it, or the computational animals are smarter than you are, so to speak. That is, you've got to a point where this system is doing things that are as sophisticated as what we can decode, or as sophisticated as any computation that can be done. At least that's the empirical suggestion that one gets. So the thing that I talk about here is that sort of why, you know, the thing that we needed to know that came out of the NKS book was not that universality was possible, but that universality is ubiquitous. That there are good indications that as soon as we get above this low threshold, we'll immediately have universality. And that instead of being some sort of very rare and special property, it is the generic property of systems that are not obviously simple. When you can't decode it, it will turn out to be universal. Now, the principle of computational equivalence actually goes further than talking just about universality. It also talks about the idea that if you are in computational universality, the question is, can you program it? Can you find initial conditions for a system so that by setting them up appropriately, you can have that one system emulate another system? The principle of computational equivalence goes further by saying that whatever the initial condition is, for sort of most initial conditions where the behavior is not obviously simple, it will be the case that the computation that goes on is also of equivalent computational sophistication. So what that suggests is, let's take something like Rule 30. We could say, well, it could be the case that Rule 30 is universal in the sense that with this very, very, very special, very complicated initial condition, we could get it to add 2 and 2. Okay, but what we're saying is even when you just give the initial condition of a single black cell, the computation that corresponds to the pattern that you get will be as sophisticated as any computation you can do. So that's kind of the thrust of the principle. I talk here in the next section about the content of the principle. And I think the first point I'm making here is that, like many other fundamental principles in science, the principle of computational equivalence can be viewed in part as a new law of nature, in part as an abstract fact, and in part as a definition. Because it tells us what kinds of computations can and cannot happen in our universe, but it also summarizes purely abstract deductions about possible computations and provides essentially general definitions of the very concept of computation. What does it mean when I say you can compute any computable thing? What does it mean to be computable? The principle of computational equivalence gives us a foundation on which to make such a statement. Now, it's a little bit like something like the second law of thermodynamics, where the second law of thermodynamics is in some ways a definition of heat. In some ways, it's a thing you can prove. And in fact, that's what I did in chapter 9, is to talk about the relationship to computational irreducibility. And in some sense, it's a law of nature about how gases happen to work and how we as observers of gases treat them. And so similarly, with principle of computational equivalence, it is a fact, it is a contingent fact about our universe that we exist in what I would now call the Roolead and not the hyper-Roolead, and that's why the principle of computational equivalence is true. Okay, so let's see, we talk about here sort of what the implication of the principle of computational equivalence might be, because what it's telling one is, yes, we've discovered this principle as a sort of empirical summarization of these things that we've observed by looking at simple abstract computational systems. But the big point here is, because we're describing everything in terms of computation, we can jump out of that abstract world and jump into the real world and say those things that are really going on in nature, in biology, in physics, and so on, those also live in the same bin. They're all computations, and they are also subject to the principle of computational equivalence. And so one of the things that will be very important here is that the physical universe is also subject to the principle of computational equivalence, and so is mathematics, for example. Now, as I say, viewed in our very modern terms of the last year or so, this fact that our universe is subject to the principle of computational equivalence is in some sense a contingent fact. It is a consequence of the fact that we exist as observers within the Roolead and not the hyper-Roolead. So, okay, I talk here about how could the principle of computational equivalence not be true, well, what does it apply to? I mean, we're talking about it applies to any kind of system. In particular, it applies to brains as well as to abstract computational systems. And as soon as it applies to brains, it tells us things about the ways that we can perceive these computational systems, and then to phenomena like computational irreducibility. So let's see, let me talk about what does it take to establish the principle of computational equivalence, to get empirical evidence. And the number one thing is prove universality. And we know the threshold of universality now in both cellular automata and Turing machines. In cellular automata, we know it that the elementary cellular automata with just two possible colors for every cell and nearest neighbors contain universal cellular automata. In particular, we know that the Rule 110 cellular automaton and its three kind of trivial equivalent rules are universal. We suspect many more elementary cellular automata are also universal, but we already know that the very simplest conceivable kinds of cellular automata contain ones that are universal. For Turing machines, something that came after the NKS book in 2007, we learned that a Turing machine that I had kind of thought might be universal in the NKS book, we know it actually is universal. And it, again, that's the threshold of universality in Turing machines, a 3-2 Turing machine, which is universal. Now, one of the things that we can do to kind of give us evidence for the principle of computational equivalence is we can look at all the other Turing machines that were below the 3-2 Turing machine. We can say, let's look at their behavior, and we see, well, actually, those ones, we can readily see that they have repetitive or nested behavior. We can throw them out. We can say those are not universal. As soon as we get to one which we cannot throw out as being obviously not universal, well, by golly, it turns out to be universal. And so that's a good piece of evidence for the principle of computational equivalence. Now, I hope that over the years to come, more and more places will find the threshold of universality. We'll be able to establish more and more pieces of evidence, or maybe we'll discover that there's some fuzziness in that, I'll talk about that a little bit later, that there's some fuzziness in that frontier, in that boundary between the universal and the obviously simple behavior. And that fuzziness might be some important area of essentially computational reducibility that we can perhaps make use of for technology. Maybe it's in addition to repetition and nesting, there's another form of regularity that might be out there that we could potentially use or make mathematics out of. And so that's, but one of the things that we can do to establish to sort of get more empirical evidence for the principle of computational equivalence is, where is the threshold of universality? And we can also, for example, the Rule 30 prizes are, again, the ways that I suspect those prizes will come out will be more, that gives more kind of testing. It's an empirical test of the principle of computational equivalence. It provides more of those in the context of just the case where, instead of saying we can program an arbitrary computation, we're just asking about the particular computation when we start off with a single cell initial condition. I talk a little bit about that boundary of what's analyzable, and point out that in chapter 10, for example, there were some examples where there were systems based on numbers, where we could use things like iterative powers to just sort of pick away a little bit at that boundary of universality and so on. I say the principle of computational equivalence asserts that these systems that we're talking about here, that aren't obviously simple, are in fact universal. And although almost inevitably it will never be easy to prove this in any great generality, my guess is that as the decades go by, more and more specific rules will end up being proved to exhibit universality. Now, I have to say, we're a little bit behind schedule on that. It's proofs of universality are always difficult and messy. They're kind of really going down to the lowest level of sort of computational infrastructure. But it will be very nice to see more of these proofs get done. And perhaps as we push forward with the field of ruleology, there'll be more energy around studying these simple systems and more ability to make those kinds of proofs. Right. So let's see. Right. So this, I'm now talking about sort of the arguments for and against principle of computational equivalence. Another question is, does nature follow this principle? Or is it the case that most systems that we observe in nature are somehow specially set up to be systems that don't exhibit computational sophistication? Well, that's a tricky one, because a lot of systems that we make use of for engineering are ones where we can foresee what they will do, and they're specifically held back from computational irreducibility and from computational sophistication. But every so often, computational sophistication bursts through. For example, in fluid turbulence, we might want to have something where the fluid flows in a very smooth laminar way, but in fact, it's very easy to get turbulent flow where things look quite random and where we are being immediately exposed to, I think, the phenomena of computational sophistication and computational irreducibility. It's also hard for us to do engineering based on that, but it's a place where in nature, we are getting immediately exposed to computational irreducibility and sort of the computational sophistication of systems. So it could be the case that nature carefully selects in some way systems that are not universal. But I don't think that that's the case. And I think it is sometimes the case that science or technology have kind of skirted around things to make sure that they only get to things which don't have that kind of sophistication. But nature itself doesn't have those constraints. And the rules it's picking are no doubt often able to show computational universality and so on. Let's see, well, I'm talking here about some more details about what kind of initial conditions you might need to show computational sophistication. This is an example showing kind of a very junior version of universality in the sense of how long does it take you in Rule 30, for example, to generate each different kind of block of with a particular form. And so this is showing, oh, I don't know, this this block here. You can see that there are it takes a while before that block is generated. This is just sort of a very junior version of universality showing up in sort of given the specifics of this initial condition, how much does that specific initial condition reach out to the generality of all possible states? And this is giving an indication of that. Okay, so that's sort of something about kind of the content of the principle, this idea that things which are not obviously simple would turn out to be equivalent in their computational sophistication. They'll all have this maximum level of computational sophistication, that applies ubiquitously both to systems, abstract systems, and to systems in nature, and to things like brains and so on. That's the idea of the principle of computational equivalence. Now, is it true? Well, so I've talked about getting evidence of the principle by looking at these questions about the threshold of universality. Yeah, this is the thing that I'm afraid happened repeatedly. People say, there's this principle, and can I nail it down to, prove a traditional mathematical theorem about this principle? Here's the thing to understand about a principle like this, and it applies to many of these general principles in science, like natural selection, like other kinds of things. The principle, almost, by the time you have really embraced the paradigm, the principle becomes almost trivial. It becomes almost self-evident. That doesn't mean it doesn't have content, but it means that it is the sort of the core of this paradigm. And it is something that once you have kind of absorbed it, it gives you intuition about a zillion other things. It gives you a framework for thinking about things. Much as in an area like biology or economics or whatever, there are paradigmatic ways of thinking about things. It is the paradigmatic way of thinking about things in the foundations of the computational view of the world. It's the foundational principle for computational X, for the computational view of everything. So, and as a foundational principle, it is incredibly important and valuable as a way to sort of drive understanding, intellectual frameworks, and so on. When you try and nail it down, it is not it isn't natural to it to be kept in a zoo, so to speak. It's not natural to be pinned down to the particular way that you describe things in, let's say, set theory. You'll have to contort that big intellectual principle into this little thing that fits in the aquarium or something. And as you do that, you may learn a whole bunch about that principle and how it works. But sometimes oh, look, it doesn't fit in that corner of the aquarium, so it can't be true, isn't a correct conclusion. It's a consequence of the fact that aquarium was built using a different framework than the one that the principle of computational equivalence, in a sense, underlies. So, okay. So, but it's still worthwhile, and people have done this a whole bunch of, can you find sort of a way of stating the principle of computational equivalence in terms of traditional mathematical logic and so on, and there are a variety of such statements that are fairly useful, and there are other ones which are just very confusing. I mean, you see these things with some regularity, people saying, I've proved it isn't true. And you say, well, what did you actually prove? Well, I'm looking at Boolean functions and their this particular case of them, and it's like, but that's not what it says. It makes a much more general statement. It is not a statement about the particulars of this. It has statements that reach into many particulars, but if you just pick your particular, so to speak, there's no guarantee that particular is one that satisfies, for example, the criterion that the behavior is not obviously simple. Okay, so, I say here, as the years and decades go by, it's my expectation that many more such discoveries will be made that are limited versions of the principle of computational equivalence. And as these discoveries are absorbed, I suspect that general intuition in science will gradually shift until in the end, the principle of computational equivalence will come to seem almost obvious, which is kind of the state that I'm in right now. And as we build this whole multi-computation structure on top of all of this, it's like, well, this is something we can take for granted type thing. Okay, so I say, as of now, the principle is far from obvious to people who have intuition derived from traditional science. And let's see. Okay, this is a good point, which I had sort of even almost forgotten, that one cause of objections, actually this objection I was sort of wrong about. This hasn't been such a common objection, has been the fact that idealizations about models of systems in nature might not follow this principle of computational equivalence, but that doesn't mean the system itself doesn't. So for instance, you could say, oh, look, I've got a fluid, it satisfies the Navier-Stokes equations. Those are partial differential equations that escape, in some ways, this sort of computational box. But then you realize, but actually a fluid is made of molecules, and the Navier-Stokes equations are just an idealization of what's happening in the fluid. So that's not the right place to look if you want to know whether nature follows this kind of computational principle. Let's see. I talk here about some more details about, it's very interesting to me at sort of a meta level. If you read something like Origin of Species, which I haven't done for a long time, but natural selection seems to us today an almost self-evident principle. But yet the book is full of, oh, but what about this? What about that? What about, and even as Darwin added additional later additions to that book, it contains, what about the objection of Professor so-and-so who talks about how pigeon breeding does this or that? Well, it turns out we don't care about any of those objections anymore, because to us now, that principle seems almost so self-evidently true that if there is an objection, well, we'll figure out how we work, how we understand and why that objection isn't right. And I think to some extent, the same thing has happened with the principle of computational equivalence, at least for me, it just is sort of at this point self-evidently true. And so these objections, while they seemed important at the time, it's like, oh, I got to explain that objection, don't really seem so important anymore. Although I'm sure that decades, centuries later, somebody will still be coming and waving a flag and saying, well, what about this objection? And then, well, yes, one can go back and look, and yes, well, that objection was addressed on page such and such type thing. This is all about continuous variables and the idea that people might say, and this was what happened until the 1980s in physics, even in the 1980s, people would say, oh, but physics is not like a Turing machine. Physics is not like computation because physics is continuous. Computers are this special discrete version. Well, I think now with our results in fundamental physics, we can really start to say, well, actually, it's the other way around. It's computational all the way down, and what emerges at the top is something that looks like it's continuous, looks like it follows calculus, has notions of continuum space, and so on. And that's the emergent thing. And people had it sort of upside down in the description of physics, where they said that's the underlying, and anything discrete is something we just build as a matter of engineering to make computers. That was the wrong way around. But that was, as I say, when I was first working on sort of a computational paradigm in the 1980s, it was, I would say 99.9% of physicists would have said, this is irrelevant, because it might even have been physicists minus countable, a finite number, so to speak, that could easily be counted, would say that was irrelevant because we know that physics is continuous. Okay, so I'm talking here about fluid mechanics, and making the point I was just making, and all of this stuff about continuum systems. Let's see, I think I have some pictures here. This is, well, okay, it's a continuum system, but, well, you could write it down in terms of digits at least, and then it's somehow discrete, but that's not right, because if you pack into a single real number packs an infinite number of digits. Okay, but it turns out, even when you're talking about continuum numbers, things aren't quite as simple as you might imagine, because what happens is that that you get, if you say, well, how am I going to prepare the initial condition? How am I going to read out the output? If you are a finite, sort of potentially computationally bounded, as we would now say, observer, well, yes, inside the system, it may be doing all kinds of fancy real number computation and so on with infinite precision, but you, as a preparer of the system, you have to prepare a finitely preparable system, and you have to read out a finitely decodable output. And so then the question is, in that translation from finitely encodable input to finitely decodable output, is it possible to have something go on in the middle that is somehow fundamentally beyond what a purely discrete computational system can achieve? And I talk about that a bunch in the notes, I think, and we'll come to that in a minute. Let's see. Oh gosh, I talk about all kinds of things here about equations and that we can talk about. Boy, this is just full of objections that I haven't thought about in a couple of decades now, because they're objections that really kind of fall away. But here's one. It says, well, we just do math around here. And in math, you write down equations and then you solve the equations. And this act of solving the equations is somehow an atomic act, as in, once you've got the equation, well, then that's tantamount to having the solution to the equation. And that's a very non-computational view. That's a very mathematics, but not computational view of things. That's sort of saying, once you have the rules, you have the answer. Whereas what we're saying in this computational setup is, once you have the rules, well, then you can run the computation, but you might still run into computational irreducibility and have sort of an arbitrarily difficult time establishing what the result is. And I point out here that if you have equations involving polynomials, then there's a well-defined way of saying, given the equation, what's the answer? But as soon as you allow even trigonometric functions, there are all kinds of undecidability issues that show up that don't allow you to even, for example, answer the question, is this combination of trigonometric functions so on equal to 0 or not? It could be arbitrarily difficult to prove that. Okay, so I talk then about differential equations. Okay, so differential equations are sort of the raw material, were the raw material for much of the kind of traditional physics-based approach to science. Traditional physics based approach to science was all, let's write down a differential equation and solve it, something which tells you the continuous variation of things continuously varying in time and continuously varying in space. So one of the things that can happen with differential equations is that when I might say, well, it's computationally irreducible to figure that out. You have to follow all the steps and just go, and spend an infinite time potentially following an infinite number of steps. You say, but wait a minute, with differential equations, you can transform the differential equation so that in finite, it will effectively go through an infinite number of steps in a finite time. So for example, if we made a differential equation for this Sapinski type thing, we could somehow transform the equation so that in finite time, finite time according to the equation, it will have generated this infinite width thing that is the infinite time output from this equation. So you say, well, how could you possibly do that? Well, an example in traditional physics is in black holes. You can have a situation where time is sort of infinitely, the light cone is tipped right over. Time is sort of infinitely extended or infinitely contracted. And you get to kind of, as you're falling into the black hole, you get to see the whole future of the universe, so to speak, from to the outside observer. It's like you're just frozen at the edge of the black hole, but to you, you're experiencing the whole future of the universe. So there's this infinite transformation between these different observers in that case. And so mathematically, you can easily represent that in differential equations and end up, and I show this picture here, where this thing is transformed into something that is an infinite, has infinitely kind of scrunched up the things as time goes forward. And so the question is, well, can that happen in the physical universe? To really know that, we have to have a theory of physics. But we can also ask the question, even if we could do that scrunch up, so to speak, can we encode and decode things for it? And I'll argue that even we fail at doing that. So Another thing I talk about here, another kind of objection, is what about human thinking? Maybe we transcend in human thinking all of these things about computational equivalence. And I argue that won't be the case. Let's see. Talking about more kinds of potential objections and so on. Let me go now to talking a little bit about the notes for this part of the book. Let's go through some of the notes for some of these early sections of this chapter, which have been talking about what is the principle of computational equivalence and why should we believe it to be true. So I think perhaps almost mocking myself here, there's a note about all this computation. I say early history of science has many examples of attempts to treat all aspects of the universe in a uniform way. In fact, that was one of the great achievements, that was one of the great insights of Greek science, was this idea that even despite the diversity of what we see in the world, that there could be an underlying that was the same everywhere. So, everything is fire and so on. And I comment here that everything is in numbers, all is number can be viewed as antecedent of mathematics, all is atoms and so on. And I'm just arguing here that all is computation, I claim, will be a fruitful new direction in science, but it doesn't mean to say all is computation doesn't mean you finished science. And in fact, I make the point that the phenomenon of computational irreducibility itself specifically implies that there is more work to be done, even though all is computation and it's all the Rouliad in the end, so to speak. That isn't the end of science. There's always an irreducible amount of figuring out of the particulars to do from that situation. Okay, I'm talking about definitions for PCE. Okay, I mean, historically, I basically came up with the principle of computational equivalence. I think I was trying to work this out because I've been writing this thing about the making of the NKS book. I believe it was in the very beginning of 1992. And I can only date it from the fact that I was living in California at the time. And I remember that the actual moment of figuring out, oh yes, this is an idea, I was sort of outside. It was very pleasant weather. So I don't really know that because it's California, that doesn't date it as much as it might otherwise. It's kind of it was one of these things where, yes, I now understand there are all these different pieces. Let me try and summarize what's going on. This is a summary of what's going on. That's the principle of computational equivalence. Okay, I'm talking here about Church's thesis, and this is sort of an interesting history of the fact that, what might be this thing that is computation? And the idea that, well, maybe it's, what will be the raw material for making anything mathematical out of? Even before one started talking about computation, what could you make mathematical things out of? And there were ideas that turned into primitive recursive functions, for example. And then there was a counterexample found in the 1920s where there was a thing which was, looked like it was a mathematical kind of thing, but it wasn't something that fitted into the particular definitions of a primitive recursive function. So when Church came along with lambda calculus, Schoenfinkel with combinators, Alan Turing with Turing machines, people didn't really know how general those things would be. Would they really cover everything that we could reasonably consider to be mathematical or later computational? Or were they merely a sort of a preliminary description that would be later overtaken by sort of a more sophisticated kind of thing? And for example, Kurt Gödel certainly thought that they had this question about whether minds were subject to the same kind of mechanical laws that other things were. Whether more specifically, he was interested in whether formalism could capture what minds can capture. And I think we now understand, with our new understanding of metamathematics, we understand Gödel was much righter than I'd ever believed that he was. But in any case, that was sort of this whole question about how would this actually apply to physics, and would it apply to the actual world, and really. as I say, I think I was much involved in making the point that it really does make sense to apply this to physical phenomena. And we now know it makes a lot more sense than even I imagined it made back in the beginning of the 1980s. Okay, we're talking about different kinds of general principles, second law of thermodynamics, relativity, Newton's laws, uncertainty principle, natural selection, etc. Okay, we're talking about how do you get out of the principle of computational equivalence. One approach is this oracles for universal systems. This is an idea due to Alan Turing, which basically said, okay, for a Turing machine, there is this halting problem. You can't know in finite time what the Turing machine will, you can't guarantee to know what it will do after an infinite time. You can't know whether it will ever halt, for example. But you can always make a Turing machine that just has an oracle. It just knows, it's caching all the data on what the halting of all Turing machines is. And that thing, the Turing machine plus its oracle, is more powerful than a Turing machine. So the question is, can that be something in our physical universe? And the argument of our physics project is no, it can't be. But that is the contingent fact that we are observers of the Roolead and not the hyper-Roolead, which would contain computations that are oracle computations, that are hyper computations beyond the kinds of computations that can be done by an ordinary Turing machine. Okay, this is talking about encodings for universality and the fact that the sort of the big criterion for an encoding to not cheat, to not put all of the kind of computation right into the preparation of the initial conditions, is to say, whatever you're doing to compute the initial conditions, it must always halt. You must be able to say for certain that that halts, and then keep going from there to say, well, what's the actual computation, which might not always halt. Talk about the density of universal systems, whether there's actually a way to estimate it, just like there's a, I think at some time in the future, there will be a way to estimate the density of universal systems, just as there is a way to estimate the density of primes among numbers. But we are quite far away from having the structure, the wherewithal to estimate that. In a sense, it's something related to the Roolead, and it's something to do with, it's not unrelated to, for example, my friend Greg Chaitin's omega constant, which is the halting probability of a universal Turing machine. This is kind of the grown-up version of that, of within the Roolead, so to speak, which pieces are capable of correspond to universality, which do not. How much of the universe, how much of that ultimate Rooleal universe, so to speak, is really universal, and how much of it is sort of closed-ended and like sort of black holes in like Rooleal black holes, where the thing is sort of closed and doesn't allow you to sort of keep going to infinity. So, perhaps it's nearer at hand as I think about it actually now, but that to me is still a, people talked about primes for quite a while before people started having a theory for the density of primes and the prime number theorem and so on. And that's sort of where we will eventually get to with the principle of computational equivalence, is these estimates for the density of universal systems. We don't have that yet. Okay, this is the proof of universality, and the fact that the proof of universality, it's in general undecidable whether a system is universal. It's like, well, I've got an encoding and it doesn't work for this kind of encoding, but let me try a more complicated encoding. You keep going, and there's no upper bound on how sophisticated the encoding may need to be that you need to sort of establish universality. Right, I'm talking actually here about Greg's omega number. This is some more detail about those occurrences of blocks in Rule 30. Okay, I'm talking here about the continuum, and about this is about cardinality in the continuum, and the question of what it really means to be continuous, and this idea that you can have countable numbers like the integers, or you can have uncountable numbers like the reals. And there's, aleph 0 is the number of is the number of countable numbers, and 2 to the aleph 0 is the number of reals, and so on. And let's see, the I talk a little bit about whether there are intermediate sets, the continuum hypothesis that there are no intermediate sets between the cardinality of the integers and the cardinality of the reals. And that might have some significance later on when we talk about other kinds of ways that one might be able to squiggle out of the principle of computational equivalence. Okay, I talk about computable real numbers here, and that's related to this whole question about how do you prepare the initial conditions for a system. This is an Alan Turing idea. The original idea for his Turing machine paper actually was this notion of, well, you've got a real number and it's like pi, for example. Well, pi is a computable real. You can say how you can compute all of its digits, but the arbitrarily chosen real number is not computable in the sense that it doesn't have a finite machine that will just go and systematically generate its digits. And that it doesn't have a finite machine is kind of a statement. You can't prepare the experiment to go and do this thing because there's no finite preparation for the experiment. And that's related to this issue of computable reals. Talking about diagonal arguments as a way to prove universality, prove undecidability. Okay, talking here about continuous computation and the question of what is needed to do that. Now, one of the things that's very interesting about that, historically in the 1930s and so on, all these different approaches to discrete computation, combinators, general recursive functions, lambda calculus, whatever else, the big surprise was they all turned out to be equivalent. So you might say, well, maybe there's another whole block of computations that are real number computations, and there'll be some way of doing those, and those will all turn out to be equivalent. And there will be a robust notion of real number computation, just as there's a robust notion of integer computation. Well, it hasn't happened yet, and it probably won't ever happen. I talk here about, let's see, I talk about this question of what you can do. Okay, so for example, I talk about register machines. Register machines, remember, are these things where you have a finite set of registers and they each hold an arbitrary integer. And you've got these programs that say, you know, add 1 to this register. If that register is 0, jump to this other instruction, et cetera, et cetera, et cetera. You might think, oh, I can just generalize those register machines. Instead of holding integers in each register, it's like in a practical computer, you could say, let's have a real number type for that register. Let's have that register hold that infinite number of digits for a real number. Let's think about things that way. Let's see. Okay. The point that I make here then is that, well, okay, you've got these infinite registers, but what can you do with them? If you just say you're doing ordinary arithmetic, it doesn't help you very much. If you start saying things like, oh, and I'll be able to solve an arbitrary equation, then that does give you some extra things. I'm talking here about Hilbert's 13th problem. There's this question of reducibility of real number operations. And Hilbert's 13th problem has to do with the fact that you can write a continuous function with any number of arguments, can be written as a one-argument function of a sum of fixed one-argument functions applied to the arguments of the original function. So it's basically like saying, if I've got f of x and y, I can somehow write that as, you know, g of h of yeah, so g of x plus h of x, or some plus h of y, or some such other thing, and that each one of those functions will be a one-argument function. And so that's sort of an example of how you start to break down potentially real number computation into something with sort of simpler primitives, a bit like a Turing machine. But that doesn't seem to work. So there isn't sort of robust notion of real number computation the same way there is of integer computation. And I think that's because it isn't really a robust notion. It's something where you live in the Roolead, you have integer computation, you live in the hyper-Roolead, you've got a whole bunch of stuff, much beyond just real number computation. There's no good way station where it's just real number computation and not a lot of other stuff. Okay, we're talking here about constructible reals, and the question of you know, what you can construct with things like ruler and compass. We're talking about universality in equations, okay. emulating discrete systems with continuous ones. This has to do with when you can kind of take a continuous system and discretize it. Now, why is that important? It's important because, as I mentioned, when we think about encoding and decoding, encoding from the discrete to the continuous, decoding from the continuous to the discrete, if this is about essentially asking the question, if you have done a kind of making the continuous system discrete, maybe that's then the whole story, and you can just talk about the discrete system. You don't have to talk about the continuous system. That's a discussion of that question. Okay, this is about the time and gravity and talking about things actually falling into black holes and things, and some features of different kinds of black holes, and this whole question about the infinite time compression in that case. Okay, this is an interesting can of worms. Okay, this is the theory of intermediate degrees. So one of the features of the principle of computational equivalence is that it tends to say that there's this, you're either below this computational sophistication saturation point, or you're at it. That is, you're either simple enough you can figure out what's going on and it's sort of simple behavior, or you're as sophisticated as anything. Okay, now, people who know mathematical logic well and theory of computation might say, but what about intermediate degrees? Okay, what is an intermediate degree? So there's this notion of computational universality, that is that you can have a system where by giving appropriate initial conditions, you can make that system emulate any other system. There's also the notion of undecidability. Given a particular system, there isn't a finite program to, for example, know what that system will do even after an infinite time. It's kind of a version of computational irreducibility. It's kind of an infinite time version of computational irreducibility. So now the question is it the case that universality and undecidability are really the same phenomenon, or is there a gradation of it, where universality is at the top, and then there's universal things, there are things which are not universal, but still undecidable, and things that are neither decidable nor universal. Okay, so at some point, when was it? 1956. It was a construction given for something which had an undecidable halting problem, but was not universal. Okay, and I give a particular picture here, which is, I think, a great simplification of the original construction that shows kind of how you get a system that is has an undecidable halting problem, but is not universal. And essentially what happens is, I will claim, is that if you allow yourself to look inside, there's a little universal thing going on inside there. It's just you cut most of its legs off. And so it's only able to kind of limp along in some specific way that can't quite reach universality, but does still get to undecidability. But I think what's going on there is it's kind of a put-up job. You're kind of, you know, you're sort of, you're duct taping a bunch of the legs together so the thing can't move them, but really it has those legs underneath. That's a very qualitative way to say it, and probably there are much more precise ways to say it in terms of foliations of Rouliads and things like that, of saying, even though the particular reference frame, and this might be a good way of thinking about it, which I hadn't thought of before, the particular good potential project for somebody, the particular kind of reference frame with which we are looking at the system is such that we cannot reach universality from it, but we can reach undecidability. But the point would then be that we can think about that as, just an infinitesimal change of reference frame, and you'll see the universality again. So that this seems like it's, but what about intermediate degrees? That's a sort of a way of evading the principle of computational equivalence, but I don't think that it is. Okay, let's go back to the main text here. So we are on to the section on explaining the phenomenon of complexity. That had been sort of the big point of the book at the beginning, was that. And really, basically what it says is the principle of computational equivalence tells us that the things that happen in nature are computationally just as sophisticated as the things that happen in our brains. And that's basically why the things that happen in nature seem to us complex. We're not able to say our brains can outthink these things that are happening in nature. Instead, the things that are happening in nature have just the same level of computation capability as things in our brains, and that's why we see complexity in the world. In a sense, it's a bit anticlimactic because we're building up to this whole thing, and then in the end, and this is the feature of the principle of computational equivalence, it's kind of obvious once you have the principle of computational equivalence that yes, well, it's obvious that things in the natural world will seem to us complex because they're just the same computational capabilities as we have in our brains. Okay, so then I start talking about computational irreducibility, and I have to say I've referred to this section of the book so many times in things that I've written about computational irreducibility. And talking here about what computational irreducibility is, this notion that you kind of can't jump ahead, or at least you can't generally jump ahead. There may be some specific freeway that you can get onto that's a piece of computational reducibility. In fact, there always will be an infinite number of those. But the general question for sort of an arbitrary piece of well, what will Rule 30 eventually do? There is no choice but just to follow its steps and see what happens. I talk here about sort of the comparison between reducibility and irreducibility. In this case, code 870, code 843, it's really straightforward to say what these are going to do. They're both periodic. We can just say, if you say, well, what's this one going to do 1,000,000 steps from now? Trivial, I just work out 1,000,000 mod, whatever the period is here, and I got the answer. Okay, now let's look at code 1599. What's that going to do after 1,000,000 steps? Well, I don't really know. Let's run it and see what happens. Okay, we run it. I'm sure I have a picture of it here. There we go. I run it, and what's it going to do? That's what it does from a single cell initial condition. What's it going to do? I don't know. This is something where it's in your face computational irreducibility. And if we do different initial conditions like this one here, let's say you run it for a while, and well, actually in that particular case, it turns out to die out. But the basic point is computational irreducibility is the story of you can't work out what's going to happen in a system like this, except in effect by following each step and seeing what it does. There isn't a formula that just says, oh, that's the answer. And computational irreducibility is the statement that what is in that situation where there isn't a computationally reduced way to find out what the answer is. And the argument for why computational irreducibility happens is just principle of computational equivalence. If you wanted to predict what the system will do, then you, in a sense, have to be able to outrun the system. You have to be smarter than the system. You have to achieve its computational output by doing a simpler computation, by doing a shorter computation. But the principle of computational equivalence tells one can't generally do that. And that's why computational irreducibility exists. Okay, so I give the argument here that computational irreducibility is the big phenomenon that science had traditionally shied away from, and that was a barrier to lots of kinds of progress in science. That like you run into something and just say, it's pretty complicated. I don't know what's doing. I don't even know why it's complicated. You realize, well, there's computational irreducibility. That's why it's complicated. So you have to kind of discuss different things that you can study about the system that don't rub your nose in computational irreducibility. Now, a big result of recent times in this multi-computational paradigm is the fact that for certain kinds of observers, it can be the case that the things they work out are not subject to have slices of reducibility within this underlying computational irreducibility. But computational irreducibility is sort of a story of why kind of the traditional notion of sort of the purpose of exact science isn't really the whole story. You know, people say, well, what do I want? What do I want to make my exact science be worth having? I want to make it predictions. I want it to be able to predict things. I want it to be able to tell us what will happen in some scientifically reduced way relative to just watching and seeing what happens. And that's, you know, that's the that's the notion that sort of the purpose of science is to be able to make these kinds of predictions. What computational irreducibility is telling one is something very surprising at first, but very important, which is all the way from inside science, kind of science is eating itself and saying, well, actually, there are lots of kinds of situations in which you can't make predictions, in which this notion of what the purpose of science is just isn't going to work. And so that's something where people say, well, look how science is limited. And people will come from science and say, no, it's not true. Science will be able to do everything. Well, computational irreducibility tells one, it shows one that's just not true. And it's something that comes out of the insides of science itself. It's pulling its science down and it's explaining its limitations. So that's kind of the effect of computational irreducibility. What is this? This is about computational reusability. This is about saying you want to know what's going to happen some number of steps in the future. You basically just feed in the coordinates, and one will have something which just takes the values of those coordinates, grinds them up, and tells one what the answer is. In this case, for a periodic pattern and for a nested pattern, showing that you can do that very, very efficiently relative to the time that it would take to explicitly work out the pattern for that number of steps. Let's see. I talk about the question of whether you could have computational irreducibility that is where you can answer some questions but not others. These are just examples of, I think this page was partly because I just really liked some of these pictures. But these are very, I don't think these have been much investigated, and there's actually a lot more that can be done on these are sort of versions of context-free language pictures showing sort of generating them that way. And let's see, this is really cases where there is a short answer, where there is a way to reduce the computation. And this is sort of examples of how that can happen. I talk here about, I'm talking a lot about kind of the boundaries of computational irreducibility. This is the case of repeated squaring that I mentioned in chapter 10. I mean, in a sense, what tends to happen with these kinds of principles and ideas in science is, if you want to know what the footnotes to whether something is true is, go look at the original thing that introduced it, because it's going to have, if the writer of it was was serious, so to speak, they're going to tell you all the reasons it might not be true. And then in the later history, people will just say, but it's obviously true. So all of those arguments for why it might not be true are kind of like, well, who cares anymore? We know it's true now. Let's see. We're talking about the question of what it means for there to be computational irreducibility, and the fact that, for example, it means that things like simulation are not just things which are convenient, they're things which are fundamentally necessary to do in studying science. So let me see, I can, let's look at the notes here. History of computational irreducibility, yeah, that's interesting. Well, they're precursors to this idea. One of my favorites is Isaac Newton quote about having invented his law of gravity, says, to define these motions. So when you've got a lot of planets in the solar system, to define these motions by exact laws admitting of easy calculation exceeds, if I am not mistaken, the force of any human mind. So, in a sense, Newton was saying, God can work out where the planets go, but no human mind can work out, even given Newton's equations, can work out where the planets go. So that was an early recognition of a phenomenon like computational irreducibility. The three-body problem, the Earth, Moon, Sun problem, was a problem that vexed many people. It was sort of a top science problem of the 1800s. And that was a case where that was sort of the minimal version of that, well, where are the planets going to go type question. And that might have led to notions of computational irreducibility. Of course, it wasn't set up in a computational way. It was set up with real numbers. It was set up in a place where you could kind of hide a lot of detail in sort of these sequences of real numbers, and you couldn't really do good accounting for what was the sort of computational effort that was involved in the thing. People, I mentioned here that things like quantum mechanics and so on, and statistical mechanics were saying, well, let's not look at the precise answers, the precise solutions of these equations. Let's just look at some statistical average. And that was then what people concentrated on, although then there was the whole question about exactly solved models and statistical mechanics. So the whole thing repeated itself. But somehow people noticed that it was hard to get exact solutions, to get formulas for things. But it was just like, well, it's hard. There wasn't really anything deduced from the significance of the fact that it seemed to be hard. Really, the significance is computational irreducibility is biting, it's biting at one, so to speak, and that's the thing that is preventing those things from being just cracked and solved, so to speak. I talk about difficulty of solving equations for numerical weather prediction, noted even in the 1920s. And people eventually concluded that the reason why weather predictions were hard had to do with knowing the initial conditions accurately, not because there was something intrinsically computationally irreducibly difficult about doing the predictions. That just didn't really come up. Let's see, talking about game theory and human predictability, algorithmic information theory. Let's see, the whole notion in the 1970s that nonlinearity, when you have linear systems, you can just sort of add together solutions, and every added together solution is another solution. It becomes rather easy, usually, to figure out what's going to happen in a system. But nonlinearity, the fact you can't do that, the fact that you can't just make solutions out of kind of elementary solutions, that was a thing much emphasized in the late 1970s, and that's a thing that is part of the same story. But the fact that was what was emphasized rather than the more general phenomenon of computational irreducibility, that was sort of a sideshow and, in a sense, a misdirection to say it's all about nonlinearity of equations. That's not really true. It's all about the fact that you're thrown into this general case of computational sophistication rather than skating along in the special case where that doesn't happen. I say here an important reason why computational irreducibility wasn't identified before is that for a couple of centuries, students have been led to think that theoretical science could always be done with formulas. And I comment on the fact that Mathematica basically was the thing that gradually led it to be the case that physics textbooks and things didn't just say, work out this exactly solvable thing that can be done in terms of integrals you can solve as an explicit solution and so on. So that was a thing which was sort of burnt into people's view of science, is if you succeed, you will succeed in reducing the result to something computationally much simpler. And it turns out that that's not true, but to the science that people were seeing and doing, that seemed to always be the case. Okay, I'm giving a list here of the history of exact solutions. It's kind of a fun list, actually, of different kinds of models from quadratic equations in antiquity to two-body problems and brachistochrons and the six-vertex spin model and et cetera, et cetera, et cetera. Different cases where it was possible to find exact solutions to things. This is an interesting point, which actually has not been explored as much as it should have been. this idea of an amount of computation, just like we can talk about an amount of heat or an amount of information. So we can probably talk about an amount of computation. The reason we can talk about that in a robust way is because of computational irreducibility, because there is a notion of a generic, and because of computational equivalence, actually, there is a generic lump of computation, and here it is, so to speak, and it has units. Well, I don't know what its units are. I think it needs units. We have to give it units. That's some, it's kind of what I was doing in the physics project. In some cases, is the units of sort of in that amount of computation. It's kind of like number of Wolfram language tokens processed per second is an analog of the speed of light in rulal space. And so kind of the amount of computation is like number of Wolfram language tokens processed type thing. So anyway, so that's kind of a measure of the amount of computation. This is about another one of these confusions that comes up about people saying, but look, I can, instead of using a cellular automaton with just nearest neighbors, what about if I add 7 colors and 2 extra neighbors? Surely I can compute more in that case. And the answer is no. And we can show that that's no because of universality. But it also, the big surprise and the big empirical surprise is that even empirically, it's pretty obvious it isn't true. Okay, that's just some details there. Wow, that's a note I forgot. This is kind of an interesting note, actually, about when you do have an exact solution, it's no good if the function you say, oh, my exact solution is this hypergeometric function. It's no good if it takes more effort to compute the hypergeometric function than it would have taken to compute the underlying system from scratch. And this is discussing the kind of tricks that are used. This is kind of a lot of how Wolfram language works inside type thing, tricks for evaluating different functions much more efficiently than you might have expected was possible. A lot of recursive algorithms for doing that. Okay. Yeah, this is talking about the history of fundamental limits on science, and why computational irreducibility is a more fundamental one than people had really discussed in the past. All right, let's keep going here. Okay, the next up in this chapter is the section on the phenomenon of free will. And this is really discussing the question of sort of been a mystery for a long time, how it could be the case that there might be a deterministic rule for a system, yet even according to that deterministic rule, there is, can one have free will in that situation? So, I think a good case in point to this, which I haven't done, but it will be a fun thing to do, is to say, imagine making a movie, and the only thing you do in the movie is you're zooming and panning around a growing cellular automaton. And if you make the movie correctly, then I think it will be the case that you will be watching the cellular automaton. Things will be growing, and there'll be a blob that grows out. And will it succeed or will it die? And there will be the same kind of human-like story that you will be telling yourself about this thing. And then, in a sense, even though it's completely deterministic, there's still that same level of kind of rich detail inside. And then, in a sense, the movie ends by zooming out, and you see it's just a simulation that's running according to a fixed set of rules, or even zooming in and seeing that. And this is kind of the impression of free will, is even though the deterministic rules underneath, the emergent behavior can be one that appears to be free of those underlying rules. Why can that happen? That happens because of computational irreducibility, that there is this sort of sharp boundary between what is the underlying rules and what is the actual overall behavior. So, back in the 1950s and things, when people made science fiction movies and they were thinking about computers, and like the computer would always do things, and you could always fool the computer. You could always tell when it was a computer and fool it by the fact that the thing just, quotes, followed logic, and was somehow doing things that were much simpler than any human would do. And that was kind of the idea that you have this system that's operating according to deterministic rules. Well, of course, then it will show simple behavior that's recognizably simple. But that isn't true. And that's what computational irreducibility shows, is that that isn't true. It's like you can readily say that little, fly or something doesn't have free will because look, it just keeps on bashing itself against the light over and over again, and we can readily see what it's going to do next. But that other creature there, even though we can record from its brain and we can see all that brain activity starting up, that creature has free will because we can't really tell what it's going to do other than by just watching its brain activity build up and seeing it do its thing. And so that's essentially what we're saying, is that free will is a phenomenon of computational irreducibility. Computational irreducibility is what frees the will from the deterministic underlying rules. It's what provides that sort of that barrier between the deterministic underlying rules and the actual behavior. The barrier is an irreducible computation. And so I'm just giving that argument here, and let's see. Let's see. I haven't looked at this stuff in a long time, but as soon as we see behavior, the behavior we see becomes more complex. We quickly tend to imagine that it must be associated with some kind of underlying freedom. Okay, that's a human assumption, because with traditional intuition, it doesn't seem plausible that real unpredictability could arise in a system with deterministic rules. And then I say that to explain the behavior that we humans show, because it does not obviously show signs of the effect of underlying rules, in the belief, without knowing about computational irreducibility, that underlying rules would lead to sort of very mechanical, obviously mechanical behavior. This is right. So this question of where does the essentially randomness of human behavior come from, and or randomness of what we do, and it's kind of in the past, people talked about fate and so on. It's the consequence of the configuration of celestial bodies or whatever else. In modern times, that's sort of given way to, it must be quantum mechanics, it must be quantum randomness or sensory dependence on initial conditions. But the point that I'm making here is that there isn't any explicit external source of randomness. The fact that it is unknowable what will happen, it's not fate coming from the outside. It's the intrinsic computational irreducibility of the phenomena that are happening inside the system. So that's sort of the description of what of kind of the idea of computational irreducibility and its effect, a very direct consequence for free will, for this notion that the actual behavior is separated by computational irreducibility from its deterministic underlying rules and determinable from them only by this irreducible computation, which is pretty much equivalent to just watching the system and seeing what it does. Okay, let's take a look at some of the notes for that section. Okay, I talk about the history of ideas about free will and the results of whether everything that would happen was foretellable by astrology or something, or some form of divination, that it was all determined, and that it was merely, the fates would determine it all. And then the question of, when you have legal systems and so on, it matters whether the fates determine it or whether the person was actually responsible for their actions in some sense. I'd forgotten all this stuff here about Augustine talking about God might have infinite knowledge of the future in a way that we humans could not. That's sort of an analog of computational irreducibility. And Augustine is saying God might have infinite knowledge of the future, as in from just knowing the rules by, it is the computation determines the future. and it does so infinitely, but us humans have to just follow the steps when we actually do the computation. Let's see, I'm talking about Hobbes and Kant and so on. The question of whether there are simple laws of human behavior. Let's see. Oh yeah, I had forgotten this description from Hayek, talking about the fact that human behavior might be fundamentally unpredictable because in effect, brains can explain only systems simpler than themselves and can thus never explain their own operation. So that's kind of a diagonalish argument that's a little bit like computational equivalence, that's saying, look, we've got to explain brains and we've only got brains to do that with, so we won't succeed in doing that. But it doesn't seem like that argument was particularly followed up. And it could be the case, as I was discussing earlier, that while that might be true that brains can't predict what brains will do, it could be the case that, for example, when organized into a society or something, brains do things that are simpler than what brains could intrinsically do, and that therefore there's something predictable about it. Yeah, I think I talk about the attribution of free will to animals increasingly happening in the 1980s and so on. And then the question of free will for computers and AIs and so on, which I think is still sort of up in the air. And I think that has a lot of consequences in AI ethics. AIs have rights, things like this. I talk about something which is, I think, not so often claimed in these years, that Gödel's theorem shows that humans cannot follow definite rules, but that's just it's just not a correct argument. I'm talking about the fact that you can start measuring what happens inside a brain, and as you home in on what's happening inside a brain, you're realizing, oh my gosh, it's actually deterministic what's happening inside that brain, even though what seems to come out seems to be free will. It comes out as a result of all of these neurons firing, and it is free only in the sense that there's computational irreducibility in going from those underlying neuron firings to the actual behavior of the person, so to speak. Let's see. That's an interesting claim, which I had forgotten I had made here, about unconscious thinking being thinking that is may involve more computation actually than conscious thinking. Well, I think that that's reflected in the whole multi-computational story, because my guess now is that the single thread of experience that we concentrate on, that's the story of computation, but there is a whole set of other threads that are all going on, which is sort of the unconscious threads, which are a story of multi-computation. And it's a story of how we take all those threads and knit them together into something which we say, this is our experience, this is what happened. That's the story of sort of multi-computation and so on. And that's that. I talk about responsibility and free will. I actually discussed this again in the piece that I wrote about consciousness and multi-computation and so on. And this question about whether saying that the reason you did something is because of something intrinsic to you, how that relates to responsibility. Let's say that we are, it is completely determined by the neuron firings in my brain what the next word I will say is, or whether I will do some terrible thing or something. It's completely determined by the neuron firings in my brain. Okay, so that's, now you say in some legal situation or something, you say, did I do that because, you could argue, well, I did that because it was something outside of me that made me do it. It was some traumatic event that happened. It was, I couldn't see the thing, therefore I did that. It was something outside me. It was some initial condition for me. It was some randomness from the environment that caused me to do that thing. And so don't hold me responsible. It was just the environment what made me do it. And so that's sort of one theory of what's going on. And people who say, well, the brain isn't really, there's things going on that are from outside the brain that affect how we think. That's kind of the don't hold me responsible. It's just the environment that made me do it. So the alternative is the thing that I think leads to much clearer ways to understand sort of human responsibility, which is this computational irreducibility story, where what's basically happening is that it is intrinsic to the system itself that the system will do this particular thing. It is off computing the digits of pi, and it's always going to do that. And if you don't like that, well, then you've got to, cart the system off to jail or something like that. It's something where the system itself is responsible for what it does in a way that's different from the environment just kicked it to do it. And so in a sense, this idea of this deterministic, I'm responsible for it, it is this computation that is going on in me, is much more of a bringing the responsibility into you than something where you say, well, look, it's free will, and therefore we're responsible. It's free will, as in nothing can predict what it will do. Then sometimes one feels that makes one more responsible, but I think quite the opposite is true, that it's when there is a thing which is known to do that, then it becomes responsible for that. Well, I talk here about free will and purpose. Things that are too predictable don't seem free. Things that are too random do not seem to be associated with the exercise of will. For example, if you have a twitch that is sort of randomly twitching, or a tremor, that doesn't seem to be an exercise of free will. The tremoring is not the exercise of free will. That seems to be something that is just signals in our brains, so to speak. And I talked here about this question of whether something has a purpose, and I will talk about that some more in later sections of chapter 12. Okay, so let's keep going. So that was a discussion about free will. Let's keep going here. We're going to talk next about undecidability and intractability. And my guess is that's the last section I'll be able to cover today. And next time we'll go through the remaining parts of chapter 12. I probably won't go through in as much detail the implications for mathematics as I might, because I've written such a big thing about that recently. And there's probably some updates to give to this, but I'll talk about that some. But let's dive in here to undecidability and intractability. Okay, what is undecidability? Undecidability is there's no finite way to know the answer to something. So for example, I've said this many times, when there's computational irreducibility and you ask a question like, what's going to happen in the end after an arbitrarily long time? There's no guarantee that you'll be able to pull that back to a finite computation to answer that question. It will take the system an infinite computational amount of effort to find the answer, and you won't be able to pull it back to make that finite. And that's the story of undecidability. And so here's an example. Let's look at this system. It's a nice deterministic cellular automaton. In this particular case, you say, what's it going to do in the end? Oh, well, after 1,000 and something steps, well, actually, this case here, what's it going to do in the end? Well, it quickly halts. In this case here, what's it going to do in the end? Well, it blobbles around for 1,000 and something steps and eventually halts. What's it going to do in these cases? Well, I don't think I even know. I trace these things for millions of steps, and I still don't know what they're going to do. And that's undecidability staring one in the face. That's the phenomenon of undecidability, is you can't know what's going to happen after an arbitrarily long time. You just can't know. That you might be lucky and find out after 10 trillion steps, you run it for 10 trillion steps, it dies out. Okay, great, you're done. But then you've got another example of the same system where it's still running at a quadrillion steps. You still don't know what's going to happen. Now, sometimes you can say, but I can see that it became periodic, and so I know that it's never going to die out. But again, there are plenty of cases where you won't see that, where you'll see sort of continual computational irreducibility, and you won't be able to know whether it will die out ever in a finite amount of finite number of steps. Okay, So I'm just talking about what happens in those particular systems. Let's see, what is this about? Oh gosh, this is a different example of undecidability. This is a thing called the post-correspondence problem. Okay, the question here is, this is a constraint-based problem. This is something that should be studied a bunch more. I put some effort into doing this, but it really needs to be looked at some more. The question is, given certain blocks, is there a way to combine these blocks? Think about these as sort of puzzle blocks. Is there a way to combine? Each of these blocks has an upper side and a lower side. Is there a way to combine block A, B, B, C, A, B, B, whatever, so that the upper block and the lower block, so that the sequences you get for the upper and lower blocks agree? Actually, it occurs to me that this is something we might look at in the context of molecular computing to try and see whether there are molecules that can be set up in this kind of way, where it really matters to the energetics, whether those sequences are, an upper and lower sequences are the same. But the question here is, given a set of blocks, is there a way to arrange those blocks so that you will get upper and lower agreeing? Okay, so there's some blocks where you can prove that there's no way to do it. There's other blocks where you can do it, but the shortest thing that achieves it is really quite long. Okay, so this is another case where it's known in general that there's undecidability. It's known that in general, it can be arbitrarily, there exist blocks where it can take, you don't know in advance from knowing what the blocks are, you don't know in advance how long it's going to take you to resolve this question. And this is a case where, again, there's undecidability. It's a rather different kind of problem from the cellular automaton problem. It's a problem based on constraints in this case. Is there a way of satisfying those constraints that has a particular way of satisfying those constraints or not? There are a whole class of undecidable problems that are of this general kind. Is there a way to achieve this? And as opposed to, does this thing ever end up in this state? In terms of mathematical logic, you can think about these things as different kinds of quantifier type expressions. Talk about the halting problem this. Right. I'm also talking about, this is another important piece. So undecidability of something like the halting problem is the question, what will happen in the end to this computation? Will it eventually halt, or will it go on forever? So a different question you can ask is, I've got this computation that I want to do. How many steps is it going to take me to do this particular computation? And can I, for example, get that computation done in fewer steps? Is there some way to, and this is again sort of tightening up the notion of computational irreducibility, is there a way to get this particular computation done in less steps? Okay, so here's a Turing machine, and this Turing machine is it actually achieves the objective of adding 1 to the digits in a number. So you'll see it's going 15, it's 1111, and it's going trundle, 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 and eventually the Turing machine turns it into 1, 0, 0, 0, 0. And the rule for this Turing machine is such that we're saying if the head ever gets further to the right than it starts, then we can consider the Turing machine to have halted, and we read out the answer. Okay, so this is, if we say, well, how long does it take this Turing machine to do these computations? This is the running time of the Turing machine as a function of the input number. And we can see that the running time has this kind of comb structure, which gradually logarithmically increases with the number that's given in the initial condition. Okay, so we can think about this as a very minimal example of computational complexity theory, as it's called, the theory of sort of how many computational resources does it take to do a particular computation. This adding 1 Turing machine, we're saying this is the time complexity of the adding 1 Turing machine, and this is the function that we get out. Okay, so here's an important point. These are different ways to add 1 to a number with a Turing machine. These are different Turing machine rules. But it turns out we can see that these different rules take different numbers of steps to achieve the same computational output. So this is an indication that a given question, it's not there will always be a shortest Turing machine that will generate the output, at least for a particular size of input. But in general, different Turing machines will take different times to generate the output. Okay, this is an interesting picture. So this is asking the question, for what functions that you might compute, is there no Turing machine that gives the answer in a very quickly? And so this is asking the flip side question. It's kind of an empirical version of computational complexity theory, where what we're doing is we're saying, let's look at all possible Turing machines that have two states and two colors, the 4096 simplest Turing machines. And let's simply ask, what functions do they compute? So some of them will compute distinct functions. Some Turing machines, like the three here, all three of those Turing machines compute the same function, but they do it with in different speeds. So here's a more dramatic example. All three of these Turing machines compute the same function, but that Turing machine there computes it in constant time, whereas this Turing machine here occasionally has these big bursts of taking lots of time to compute it. So what's interesting here is that, and by the way, something that can happen is sometimes a Turing machine will be great. It'll compute the function just fine for many values of the input, but sometimes it will just never halt. By the way, this is a picture which absolutely would be worthwhile to do projects to study generalizations of this picture. This is the case of what's usually called a partial function. If it halts, you're all good. If it doesn't halt, well, unfortunately, that case didn't work, but don't hold it against the function, so to speak. So this is anyway, this is kind of an empirical version of computational complexity theory, where we're saying the flip side question. Usually it's given a problem, what's the simplest Turing machine that will compute it? This is given these simple Turing machines, what problems do they compute? What functions do they compute? And how long does it take to do that? And which of them are equivalent in the functions that they compute? Okay, so this whole question of, are there functions that are intrinsically hard to compute? That's kind of like these undecidable questions, like, does this Turing machine ever halt? These kinds of things. Is it the case that there are functions that are intrinsically hard to compute? And so these are examples of cases where, for example, these are cases where we're looking at a Turing machine and we're looking at different possible inputs. So we're encoding the input as a sequence of digits from, let's say, a number in the initial conditions for something. And then we're saying, how long does it take this Turing machine to halt in our definition of halting, which is that the head goes further to the right than it's ever been before. And what's interesting here is that some of these Turing machines halt very quickly, but some of them blob around for a really, really, really long time, sometimes exponentially long, before finally halting, and some of them don't halt at all. And so this is a way, so this is showing these functions, and I think maybe I have another example here. Do I have another example? No, I don't actually. This is examples of kind of the computational complexity of doing different kinds of things and how long it takes things to halt. There are 4-state, 2-color Turing machines that exhibit exponential growth, again, something that should be studied in more detail. But this is asking the question, is it the case that there are systems where computing that function within this class of systems necessarily takes a long time? Now in computational complexity theory, the big goal is to prove a lower bound, to prove that this particular computation, there's just no way to do it in less than such and such a number of steps. Most of the lower bounds that are known so far are ones that are very mechanical, in the sense that, you can't multiply two numbers together in less than order n steps, where n is the number of digits, because after all, we've got to read every digit to know what the product is. The initial versions of that were like n squared, but it's now down to n log n and so on time. And so this question of, there's this question of, can you find a lower bound on computation? Well, finding it by proving that there is no algorithm that will compute this particular function any faster, that's been often a losing battle because A, it's hard to make such a type of proof, and B, people come up with cleverer and cleverer algorithms which suddenly take things that look like they should be exponential time. I don't know, finding primality or some such thing, different from factoring, but finding primality is known to not be exponential time. That's known to be polynomial time, but it needs a fancy algorithm to show that. And there are many other examples of that. This kind of empirical computational complexity theory, where you're just saying, let's look at all these systems of a particular type, and let's find the one that computes a given function fastest, then you have no doubt that really is the simplest the fastest such function. Now, what's interesting here is, let's take this example here, where this is the winning Turing machine. That's the fastest way to compute this function. But one of the things that's tricky is sometimes the sequence of values of how long it takes to compute is very, very messy. And so if you were solving, and this is related to the P versus NP problem, if you were trying to show that no, this particular thing is kind of a lower bound on how difficult it is to do the computation, it could be that for almost all cases, for every case in the first million cases, all but one of them can be computed really quickly, but one is really messy and takes a long time. So there's a lot of complicatedness and kind of limit that has to be taken of saying, well, what about, the limit? Is it the case that all possible versions of this take exponential time? Well, you end up with a bunch of undecidability questions about whether this curve chased that curve in that particular way. So I talk about other kinds of systems here, like a Turing machine emulating a cellular automaton. I talk here about multi-way systems, actually, and the fact that a Turing machine could easily check a path in a very short time, but to determine whether a path exists could take exponentially longer. And that's a fundamental fact about multi-way systems. It's the fact that leads one to hope that quantum computers could do things, because in quantum mechanics, we think that it's sort of following a multi-way system. It's tracing out many possible histories. And so you say, well, let's make use of that to do computation. The big issue, as we've now understood, is that, great, you can compute the answer on some branch in the multi-way system, but to knit together those branches and be able to say, look, that's the answer, here we found the answer, that knitting process is itself computationally expensive. And that's where there's a challenge in kind of making practical use of things like quantum computing. Let's see, what else do I have here? I'm talking about non-deterministic Turing machines here. I should probably reread this section, actually, because it's very relevant to the things we're talking about right now in observer theory and so on. But I'm talking here about a non-deterministic Turing machine, and right. This is the translation. This is the kind of, I'm talking about NP completeness, which is the kind of finite time analog of universality, or one of them. And it says that an NP complete problem is a problem which has the property that you can encode any other NP problem within that problem. So let's say that we could solve the problem of the traveling salesman problem. We could solve the graph tiling problem, and we could solve the satisfiability problem. One of the things that, again, it's a bit like the discovery of computational universality, was discovered in the 60s and 70s, is that those problems are all equally hard. That is, if we could solve satisfiability fast, then we could encode a tiling problem as satisfiability, and then we could do that one fast as well. So all these problems are equivalent. They're encodable within each other by quite straightforward encodings. And so they're all equivalent in their computational sophistication, in a sense. It's a story like the principle of computational equivalence, that it's a story, and there's probably a version of the principle of computational equivalence, actually I hadn't really thought about this recently, that could be formulated in terms of NP-complete problems, about the fact that any problem of a certain type will generically be NP-complete. Well, okay, so this is a case where we're looking at the comparison between a non-deterministic Turing machine and a cellular automaton. And let's see, this is asking the question, I think, does there exist? What is this? Oh no, this is showing that you can make a cellular automaton emulate a non-deterministic Turing machine. It's showing that you can kind of encode the non-determinism in the states of the cellular automaton, and that you can kind of go that way round of emulating although it takes exponentially long in general, emulating a non-deterministic machine with a deterministic cellular automaton. Oh boy. Yeah, this is one of these, that's a really complicated diagram. Yeah, this is one of these things where it's sort of a challenge to make a self-evident diagram of this phenomenon. This shows the correspondence between satisfiability and non-deterministic Turing machines. So satisfiability, this is the longest caption in the book, for better or worse. Satisfiability is the problem given a Boolean expression, something like P and Q or not P and not R, et cetera, et cetera, et cetera. Given a Boolean expression, does there exist an assignment of truth values to P, Q, R, et cetera, so that the expression is true? And what this picture is showing is how you can translate that problem, which is being represented. Oh boy, I have to read this here. Each row can be viewed as a term in the conjunctive normal form of a Boolean expression. So I think that's up here, I think. I'm not certain how this picture works. Exercises, go decode this picture. But basically what this is showing is that the question of what a non-deterministic Turing machine can do is equivalent to the question of satisfiability for a Boolean expression. Yeah, that proof is often kind of complicated, but this is makes it, if you understand this picture, for which you have to read part of this caption here, it makes it almost self-evident that those two problems are equivalent. Okay, so this is asking the question in the cellular automaton, a question that is an NP question is, given a sequence of cells in the cellular automaton, what is the initial condition that gave that evolved to give that sequence of vertical sequence of cells? And you can clearly find that out by just enumerating possible initial conditions and seeing whether you get that sequence of cells. The question is there a better way to do it? That's one question. Another question is that problem of inverting from the vertical sequence to the horizontal sequence NP complete? And the answer is that in general, for an arbitrary cellular automaton, it's not hard to show that that problem is NP complete. So now the race is on, just like the threshold of universality, the race is on for the threshold of NP completeness. Whereas what particular rule, what particular cellular automaton will be the simplest one for which that inversion problem is an NP complete problem? And for example, is rule 30 something which has an NP complete inversion problem? If it does, it's probably very relevant for cryptography, because cryptography is a story of trying to use problems that are in NP and hard, like factoring, where it's easy to multiply numbers together but hard to break them apart into factors. That's the same kind of thing here. It's easy, given the initial conditions for the cellular automaton, to run it and see what the vertical column is, but it's hard, given the vertical column, to deduce what the possible initial conditions might be. But so in the general case that's NP complete, the race is on to figure out, for a particular cellular automaton, is it NP complete? Another good project for somebody to work on, actually. So this is sort of showing the empirical difficulty of that problem for rule 30, of when you get which sequence of cells given the initial condition and so on. Sort of, if this was obviously visually simple, then it would kind of tell one immediately that this is not likely to be an NP complete problem. Okay, let's have a quick look through the notes for this section, of which I think there are many. Oh boy. Well, all right, let's see what we can do here. Okay, history of undecidability. This is the story of Hilbert, who thought that you might just be able to write down the axioms of mathematics, and then that would be tantamount to like solving all of mathematics, to Gödel showing that that wouldn't work, to a variety of kind of clarifications of that came subsequently. And I guess in physics, the whole thing was introduced by this paper that I wrote in 1984 called Undecidability and Intractability in Theoretical Physics, which was kind of an attempt to apply this kind of a pivotal paper in terms of using computation to talk about physical systems. And that's kind of the place where I think all this work on computation got kind of attached to thinking about physics. And sort of the physical version of the Church-Turing thesis is kind of the thing that's spelled out in that paper. I think hadn't really been spelled out before. So about undecidability, what's the relationship between undecidability and classic mathematical impossibilities, like you can't trisect an angle, you can't square a circle, things like that? In a sense, those are very junior versions of undecidability, in which you're saying that with a particular set of constructs, like ruler and compass or something, you can't put those together in any finite sequence to achieve this operation of trisecting angles. But it's a slightly different case from the full case of undecidability with arbitrary computation. That's talking about the particular cellular automaton that I talked about being undecidable and showing what happens after 15 million steps. And you still can't tell what it's going to do. This is about halting problems. Proofs of undecidability. It's really about the kind of the structure of proofs and being able to prove them by contradiction and by things like self-referential paradoxes. I find it much better to just think about it in terms of computational irreducibility and say that in the end, the real hard point is that as a predictor of the system, you can't infinitely speed up the prediction of the system because there's irreducibility. You can couch that in different terms in terms of diagonal arguments and so on, but it all boils down to the same thing, that the system can't outpredict itself, so to speak. The system can't outpredict. If the system is equivalent to all other systems, then it's like asking the system to outpredict itself. But that's all tied up with this principle of computational equivalence in something that's much more intuitively about you can't infinitely speed up an irreducible computation. Examples of undecidability, these are some sort of classic examples: mathematical logic, undecidable whether statements are provable from an axiom system; combinatorics, undecidable about whether tiles can tile the plane; whether strings exist that satisfy conditions; Diophantine equations, are there integer equations, which we'll come to that in the mathematics section; are there integer equations which have solutions, finite solutions, and so on. I end here by saying it's in general undecidable whether a given system exhibits universality or in fact whether it exhibits undecidability. There's no guarantee of a finite proof of that. I talk about undecidability in cellular automata and various kinds of problems that can be proved undecidable. Undecidability in natural systems, it's sort of interesting actually, and there's probably more that should be done on this. The undecidability of the equivalence of four manifolds, that has various sort of immediate consequences in traditional mathematics, although I think that's less interesting now probably because of the fact that we're thinking about space-time in this more network kind of way. I think this sort of the formal mathematical undecidability results about arbitrarily finely delineated four manifolds are probably perhaps a little less relevant. One that is really a holdout that I am certain is going to be undecidable is the three-body problem, the Earth, Moon, Sun system. I'd shown in chapter 7, some pictures of the sort of the complexity of the orbits of the three-body problem. And it's kind of an in-your-face, this is going to be undecidable type question. And the question is going to be, given a planet, given three self-gravitating bodies, injected into a system with certain precise velocities and positions, is it decidable what will be the outcome, whether there will be two planets orbit, two stars orbiting around each other, and then the third one is escaped or something different. There's an irreducibility question, which has to do with, can you speed up this computation? And there's a universality question. Can you encode in that computation an arbitrary computation? I'm sure you can. It's just very tricky to actually figure it out, because it's a story of encoding what's essentially real number initial conditions in this encoding kind of discrete computational, obviously computational questions in the system that has real number initial conditions, and that's just tricky. So that's a case. Let's see. In biology, I mentioned formal models for neural processes can be undecidable, like whether a particular stimulus will lead to a given response. It'd be fun. I wrote that before deep learning became a popular thing. It will be fun to go and try and look at that in actual neural nets, in simplified versions of actual neural nets, and see what kind of whether you can make an idealized model there where you can say it's undecidable whether it's going to determine this is a cat or a dog. Most non-recurrent neural nets are just like it's a feed-forward network, and it just does what it does, and it takes constant time. But if you have recurrent networks, you can get these things where it's more complicated. Okay, this is an interesting one. Formal models for morphogenesis can also involve undecidability, so that, for example, it can be in principle undecidable whether an organism will ever stop growing, or whether some given given structure can ever be formed. The problem of cancer is basically the problem of a halting problem. It's a question of, given this particular set of rules for these cells, will those cells eventually halt and make a thing of finite size, or will they just keep growing forever and eventually take over the system? And that's essentially a halting problem question. And that becomes a question which, if we had better sort of theoretical biology, we could say this particular genome with this particular modification of the genome or different methylation pattern or whatever it is going to be one that grows forever, and this one isn't. So it's like, there might come a time when we can when in principle we could say, don't use a Petri dish, use just look at the sequence and see what will happen. But computational irreducibility and undecidability is going to bite one on that. It's going to say, well, actually, you can't know. This thing could keep going and blobbing around. It is not doing very much. And then suddenly, after 5 years of growth, it suddenly zooms off and starts growing forever. And it's hard to know that. That's interesting. Undecidability in Mathematica. Undecidability in set theory. This is a somewhat technical kind of issue. Tiling problems, I mentioned those earlier, in chapter 5, systems based on constraints. This is pointing out that in a two-dimensional tiling problem, it is in general undecidable, but a one-dimensional one of whether you can label, sort of have these one-dimensional blocks, that's always decidable. Okay, this is talking about these correspondence systems. This example, this is more detail about the post-correspondence system. This of those things where we're saying, can the upper and lower ever agree? Boy, there's nothing new under the sun. So this is about multi-way tag systems. And I completely forgot this notice here. Tag systems are these systems where, well, you can see the rules here. You chop the letters off at the front and you add them on at the end. This particular one is one that Emil Post studied in 1921 and that I wrote about extensively last year, and where we still don't actually know what, the long arm of undecidability has reached in and burnt a very large amount of computer time, for me at least, trying to determine whether, in fact, this thing always halts or not. And we have examples where it does halt, but it takes it billions of steps to halt. But we don't know if there's any case where it never halts, although I strongly suspect there is. But I didn't remember that I had considered the multi-way case of tag systems. I don't think I've ever really studied multi-way tag systems. It's another good thing to look at, although maybe I've looked at it a bit in the context of the study of the post-tag system. Okay, word problems. This is related to the post-correspondence problem. And the question is, given a set of relations between words, like you say, this is equivalent to this, and you're concatenating, you're making a string that's a concatenation of these pieces, but then you can make these transformations. Can you ever get from one word to another? Is there a way to get from one word to another? This is something that came up in the metamathematics work that I was recently looking at. This question of is there a way to get from one word to another is a question of is there a proof that will get you from sort of one expression to another expression. We'll talk about that later in the mathematics section here. But this word problem question is, there's a question of, in group theory, for example, are there groups with undecidable word problems? The answer is yes. That was basically shown by Turing. But the question of what is the simplest group with an undecidable word problem, that's not really known. The best examples are really complicated. That would be a great thing to be able to figure out sort of an indicator for undecidability of the word problem in groups. A good project, again, to study that. Let's see, I want to get through these. Okay, this is string equations. We actually finally have some package for doing this in Wolfram language. It's a surprisingly complicated algorithm. It's the question of, given if you say that, if you say XX equals, I don't know, XYX equals YX, where those are capital X's and Y's, so to speak, find me letters, find me sequences of A's and B's that you can fill in for X and Y that make that string equation true. Surprisingly difficult to solve. This is talking about types of fast algorithms and various recursive tricks for making fast algorithms. It's talking about one case where you can explicitly study sort of what's the fastest algorithm to doing something, which is a sorting network, where you simply ask, I've used this example now many times, where you simply ask, given a set of elements and you're only allowed to swap pairs of elements, how many swaps do you have to do? And at every swap, you can say, is this swap a swap I have to do, or are these things already in order? And the question is, how many swaps do you have to do to be able to sort things? And the answer is, for small, for one up to, I think, size 16, if I remember correctly, one could just find what the minimal algorithm, what the fastest algorithm for sorting is. And what's interesting is it's not a very regular looking thing. It's a thing that looks really random. A little bit like some of those Turing machines that were potentially the most efficient Turing machines for particular functions look kind of random in the way that they operate. This is an interesting result, that optimal is often random. Or it often looks random, which makes things like P versus NP look potentially very hard to prove, because the thing that really is, oh yeah, I've got this great solution, but it's kind of random and it's hard to prove what it does, and it can be undecidable to prove in general that it does the right thing. Okay, this is about computational complexity theory and about the definition of P and NP and P space and things like this. History of computational complexity theory and the discovery of NP completeness. Lower bounds on computational complexity, and the very rare cases in which, let's see, in which there are lower bounds known that are mostly pure information theoretic lower bounds. If you to multiply numbers, you have to be able to read each number. But there are few cases with Boolean expressions. I mentioned one here, that XOR requires exponentially many terms if represented as in terms of ors and ands and nots. Algorithmic complexity theory we talked about before. This is, okay, these one-sided Turing machines that I'm using to do these halting problems. This is a little bit of technical detail about those. This is about the Turing machines that I showed. This is what I showed in the main text, was how long it takes those Turing machines to halt. What this is showing is what functions do those Turing machines compute. That is, once they've halted, you can look at the transformation. On the x-axis, you can give the number that corresponds to the initial condition on the tape. On the y-axis, you can give the configuration of the tape, the number which corresponds to the configuration of the tape when the thing finally halted. That's a particular Turing machine. You can see it's rather complicated to characterize what it does. There's a much more horrifying example that might be coming up here. This is figuring out what the longest halting times are for certain Turing machines and the fact that they can be exponential. Sometimes they are even multiply exponential. Okay, this is a good horror. Turing machine 600720, a little tiny Turing machine, right? Here it is, case H, it said there. Is that it? That's it. Wow, just this thing here. Look at that. How could that be complicated? That looks like, I mean, something like this, it's like you can imagine, oh, that's going to be really hard to figure out. But this guy, it looks like it's just real simple. Looks like it's really, just you could directly figure out what it's doing. Well, this is the figuring out of what's doing. What a mess. Look at these numbers that show up. This function is the integer exponent function of this thing here with 786i plus 900i squared plus blah, 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 blah. And, and here are the conditions, and it's this whole complicated recursive thing. Isn't it amazing that from such a simple Turing machine, there is a way to mathematically nail down what that machine is doing, but that way of doing it is incredibly complicated when written in terms of traditional mathematics. And this is a great example of that. It'd be lovely to have some other examples. It's a good exercise to try and make some other examples like this, where there are systems that seem like, well, they're just about on the edge of being describable. How can you actually describe them? Okay, NP completeness, examples of NP complete problems. There are many. From does a matrix have a permanent of a given value to can a multi-way system generate a certain string in a given number of steps? That's one we're going to show up again in the mathematics section quite a bit. NP completeness in natural systems, if you have something like DNA strands, folding of DNA, there's some formal versions of NP completeness there, spin glasses, other such things. That's actually an interesting claim I make here, that the series approximations grow rapidly in complexity. In any case, NP completeness of in these formal systems, formal models of natural systems, it's a question of what does it actually do in practice? If it's NP complete to solve this tiling problem, but that's how you make a crystal out of the substance, what actually happens in practice? Well, what happens in practice is the thing won't solve it. If, instead of it turning into a nice crystal, it'll turn into a blob of tar, where the thing has just put the molecules all higgledy-piggledy, so to speak, not nicely arranged in the crystal. The nice arrangement in the crystal, it could do, but it would take somehow some very long time to do it. And in practice, that's not what you get. And so nature isn't solving these NP-complete problems. There are some ways of making spin glasses, what people sometimes call quantum computer. A version of quantum computers is basically doing a spin glass and trying to find essentially that lowest tiling state in a spin glass system. And that, the question is, do you get tar or do you get the lowest state, so to speak? And that becomes hard to tell, but that's the challenge. P versus NP questions. This is the question of whether the P versus NP problem is resolvable within the axiom systems that we currently have. I suspect it may not be. Implementation of non-deterministic Turing machines, that's the satisfiability function here in terms of a Turing machine. That's turning a non-deterministic Turing machine into an expression, into a Boolean expression. Density of difficult problems, like if you've got the post-correspondence problem or a tiling problem, are most of the problems easy, but just a few are difficult, or is it sort of uniformly difficult? One knows the answer for some cases. Inversion of Rule 30, this is a little bit more detail. Okay, this is a basic description of quantum computers. Actually, I think it's a pretty good description of quantum computers, written at an intermediate time. I first worked on quantum computers around 1980, 81, and this was written in around 2000. So that's 20 years, and now we're 20 years later, and I can say things a bit more clearly, but I think there's a pretty good intermediate step there. Let's see, a few more things about I think these are various this concept of P completeness is a quite relevant concept in terms of tightening up computational irreducibility. All right, so that's what I was going to get to today on chapter 12. I see that there are some questions in the chat. Let me see if I can answer some of these quickly. Kelly was asking, what's the minimal rule set? Not sure what that's referring to. Zayden is asking, what's the difference between computation and a physical process? Hey, great question. You know, I wondered that in the 1980s. I don't think there really is a difference. That's what we're learning from realizing that physics is computational all the way down. But in the past, people said a computer is that thing that we specially make to have discrete levels and so on, but physics is something different. Let's see. Does computational equivalence imply a mathematical equivalence between the observer and the universe? Yes, absolutely. And that's the whole story of what we're working out. Computational irreducibility. Anders asks, is computational irreducibility related to entropy? Yes, I talked about that a little bit when I talked about chapter 9. The basic point is entropy is how many states are consistent with the constraints we know on a system. Well, to know with the constraints that we typically use, computational irreducibility kind of will make things be sort of random with respect to those constraints. More to explain, but basically, computational irreducibility is what finally explains the second law of thermodynamics. RBS asks, why is it difficult to prove that something is universal? It isn't always difficult. It's just that there's no upper bound on how long the proof can be. It's like saying, can you find an encoding? Can you find a way to encode any Turing machine in the system? Well, we didn't find any encodings of length 10. We didn't find any encodings of length 1,000, 1,000,000, whatever. But there might be an encoding of length 1,000,000,000,000. We don't know. But it might also be that there's an encoding of length 20 that's really easy to see. So that's the reason why it can be difficult. Let's see. What is the field of science, Parmenides asks, that creates all those curves they tried expanding ruler and compass with? Yeah, I mean, that's partly a theory of linkages, as you mentioned. I think it's an interesting question, sort of at what point, when you think about universality and you think about universality of drawing plane curves, let's say, what are the raw materials that you're going to use? And is there a robust sense in which you get just these things and no others? Is that a robust set? And that's the big surprise in computation that wasn't obvious in the 1930s. And I don't know what the analog of that is for plane curves. Okay, there's a bunch of questions here about free will. Let me not dive into that here, because that's going to be a long discussion. And I think we should wait for next time. And next time I will go over the remainder of chapter 12. And I might also take a look at some of the ancillary material in the NKS book, the general notes, which have some very colorful things in them, the colophon, the preface, the acknowledgements part of the preface, which also is quite interesting, and other things like that if we have time next time. But otherwise, mostly next time we'll be going over the second part of chapter 12, Principle of Computational Equivalence, heading for the final kind of, it's 20 years since this creature was produced. And right now I'm actually writing a description of the making of this book. I have to say it's been a bit of a frustrating experience, because I thought, I lived that decade making this book, and I thought I knew what had happened. And then as I go back, it's one of those cases, I think it's sort of interesting to ponder as a general matter that when you live through history, you're just living it day by day. And whatever arc that connects those days exists, you do not notice. You're living down at the level of the sort of the individual steps, so to speak, and the arc of connection is quite invisible. And so when you come back later and you try and say, well, why did that really happen? What was the arc that led that to happen? Then you realize different things. And that's what's happening to me now. And I'm a little bit surprised and shocked at these arcs of history that I'd never really noticed about how various things happened in the construction of the NKS book. All right, well, I should wrap up there. So thanks for joining me, and hope to see you on another live stream or next week, same time and place.